Hello everyone, welcome to our presentation on our dynamics diving project. We're Group 10, comprising of Andy Chang, Katarina Freda, Dominic Henrys, and Anna Young. Taking a look at the agenda for our presentation, we'll start with a brief introduction to the project and its goals. Next, we'll discuss the principles of diving dynamics and introduce the human model that we used for our analysis. From there, we could dive into the center of mass and moment of inertia matrices and explain how they were calculated. We'll also outline the initial conditions that define the center of mass velocity and the response for the simulations. Following that, we'll discuss the simulation of 3D rotational dynamics, our visualization method, and show the resulting dive visualizations. And finally, we'll wrap up our presentation with key takeaways in the conclusion. So, why undertake this project in the first place? Well, the project being 10% of our grade definitely motivated us. The main purpose of the project was to better understand, analyze, simulate, and visualize the dynamics of a diver, or the dynamic principles that go into diving. On top of this, we got the chance to apply topics that we learned in class and further our understanding of dynamic topics. So, what sort of dynamic topics did we get to apply in this project? We got to apply concepts of center of mass, moments and products of inertia, translational and rotational dynamics, 3D motion dynamics, MATLAB visualizations, and a lot more that we compiled together for the final result. So let's move on to the setup of our actual dive. What sort of diving did we examine in this project? So to clarify some things, we used a 3-meter springboard, a human diver that was a simplified system of rigid bodies. We used 4 different diving configurations that the diver would transition from, as well as a changing number of flips during the dive, and changing when the configuration changes happen. So this would alternate.
Our human model for this project was comprised of a series of rigid bodies, the first being a sphere for the head, which accounted for 8% of the total mass, a cuboid for the torso, which comprised 50% of the total mass, 2 cylinders for the upper arms, which were 3% of the total mass each, 2 cylinders for the forearms, which comprised 3% of the total mass each, 2 cylinders for the legs, which comprised 15% of the total mass each, and our human model as a whole was 60 kilograms in mass and 132 pounds on Earth in weight. We assume the mass is evenly distributed throughout each body part here for our project. We used 4 different configurations for our human model, the first being the standing configuration, which was used primarily to compute the original center of mass. Then we have our open configuration, our pike configuration, and our dance configurations, which were used for the actual dive simulations and visualizations. The first step to calculate the center of mass is to calculate the center of mass for each body part with respect to a common origin. In our case, we use the center of the torso as our common origin. The second step to calculate the center of mass would be to combine each body part's center of mass, taking into account the percentage of the total body mass. For example, the torso contributes 50% of the total body's mass. And finally, you'll need to repeat the 2 previous steps for each of the body configurations. The first step to calculate the moment of inertia matrix is to calculate the moment of inertia matrix for each body part with respect to their center of mass. The second step would be to use parallel axis theorem to find the moment of the inertia matrix for each body part with respect to our common origin, which is the center of the torso. The third step would be to sum the moment of inertia matrices for the final moment of inertia matrix. And finally, you'll want to repeat the previous steps for the open and pike configuration, as well as repeating for the dance configuration, and you may have to introduce a transformation matrix to account for the rotation of the limbs. Here you'll find the center of mass and the moment of inertia matrix for the standing configuration. Here you'll find the center of mass and moment of inertia matrix for the open configuration. Here you'll find the center of mass and moment of inertia matrix for the Pike configuration. Here you'll find the center of mass and moment of inertia matrix for the Dance configuration.
So for the initial conditions for center of mass velocity and response, in phase 1 we basically had to calculate the initial velocity and initial angular velocity in the situation described by the image. So to calculate the initial velocity, we use the equations of motion whenever the acceleration is constant, and the equations for the conservation of energy, since the total energy remains constant even though the kinetic energy and the potential energy vary throughout the dive. So this way we managed to calculate both the initial velocity and the time taken to complete the dive, and then we use the time taken to complete the dive together with the total angle from initial to final position to calculate the initial angular velocity. So phase 2 instead consisted in examining a dive that changed configuration from open to pike to open again, and calculating the initial conditions for the center of head and the load on the neck. So the calculations of the velocity and acceleration of the center of head were done by utilizing the following concepts. In particular, the known velocity and acceleration of the center of mass, the calculated angular velocity and acceleration, the 2-point formulas for both velocity and acceleration, and the conservation of angular momentum. To calculate the load on the neck instead, it was just necessary to basically normalize the acceleration on the y direction by the gravitational acceleration.
So for our simulation of 3D rotational dynamics, the first thing we need to do is set our initial conditions. So our initial conditions include our total time for the simulation, our initial angular velocity, our phi, our theta, our psi, and our x and y initial angular velocities. We also initialize our state for the ODE, or ordinary differential equation. The next thing we do is we create a function to compute our angular velocity and acceleration. After that, we initialize our moment of inertia matrices for our open, pike, and dance configurations, and we calculated those moment of inertia matrices in phase 1. The next thing we'll do is we initialize our configuration time percentages. So we will be in the open position from 0 to 5% of our dive. We will be in the pike position from 10% to 70% of our dive. We'll be in the dance configuration for 75% to 90% of our dive. And we will be again in the open position from 95% to 100% of our dive. Next, we will calculate the transition moments of inertia. So we will calculate those matrices with the equations in MATLAB. So the next thing we'll do is we'll create our dive simulation logic, which computes our moment of inertia matrix and our moment of inertia dot matrix for each moment in time. After that, we'll create our variables for Euler's 3D dynamical equations. And next, we'll create our rotations and compute t dot and omega double dot. And then finally, we will solve our ODE and compute the number of flips and the number of twists. So here we computed our number of flips and twists for phase 3 part 1, phase 3 part 2, and for phase 2 using our 3D rotational dynamics code. The negative values here are just an indication of direction. You can't really do negative flips, you can only do positive flips, so it just indicates the direction. So for phase 3 part 1, we computed negative 2.3006 flips and 0.8460 twists. Now for our custom dive in phase 3, or our perfect dive you could say, we computed 2.51 flips and 1.0233 twists. And finally, we verified our results from phase 2 using our 3D rotational dynamics code, and we got 2.5008 flips and 0 twists.
For visualization methods, MATLAB was used to plot and render all of it. In 2D, patch and rectangle and lens space are really important, especially patch since you can rotate patches, and the rotate, plot, and draw now functions are all really essential to getting the visualization to work. For phase 3, some more complex functions like ones to control the camera were used, as well as fill 3, which generated multiple patches to make a 3D shape. In these snippets, you can see how some things like the axis and center of mass path got defined, as well as an example of fill3 being used, and the loop used to modify all of its patches. Here you can see a real-time visualization of the diver position and orientation in phase 1, as well as all the dive stats on the right. And then here is a visualization of the phase 2 105B dive, which shows the pike position and the transitions. And then you can see stats again on the right. And then for our custom dive for phase 2, the visualization was a really important tool in getting it, because we could just tweak around when the positions would change in order to see the amount of flips and orientation. But yeah, it's not in actual time, but you can see the stats and the visualization here. Then for phase 3, the visualization was in 3D. So to simplify it, the diver is now represented as a cube or parallelepiped, depending on the position. And then you can see more information in the key and on the right. And then lastly, this was our tweaked nice dive for part 3. There's a isometric view on top and then a front view on the bottom. The key and dive stats can also be seen on the slide.
So, overall, what did we gain from doing this project? Well, as stated in the introduction slide and as reflected in our project, we got to apply topics that we learned in class. We got to model real-world dynamic systems. We translated some theoretical concepts into practical applications. We gained experience with optimization, performance tuning, and refining models. And we got the opportunity to strengthen our simulation and visualization skills by using MATLAB to achieve a final cohesive result, as well as visualizations. And we'd like to give a special thanks to Dr. Patel for assigning this project and giving us such a great semester.
Thank you for watching our Dynamics Diving Project final presentation. This is Group 10, comprised of Andy Chang, Katarina Fratta, Dominic Henrys, and Anna Young.